Yesterday and then city dot city ID, really describe that, and then address ID.
So I have any questions on what for are you planning to conduct any OH today, either today?
I posted on Piazza the recitations that I know about.
Okay. No, but the officers
What office hours for what?
for like for
Oh,
it's not been disposed to. Yes.
let me think about it for a minute. All right, so I'll make an announcement at the all right. All right, let's get this over with. All right, let's get this over with. There's one more programming question. And this is on graph database versus relational. Problem statement is use the database from homework 4. And you can use the Neo4j browser and attach and paste the displayed graph in the answer. So part 1 is write a cipher query that shows all nodes and relationships with path length 2 or less, starting at nodes that are fans and ending at nodes that are teams. And that query is basically this. So match, I want to return a path. The path starts at a node with label fan. The path ends at a team. I didn't care about the direction, so I didn't put any arrows on there. And there can be 2 relationships in the middle. So that's the query that'll do that. It's basically, what's the type that I'm starting with? What's the type that I'm ending with? And I want 0, 1, or 2 relationships in between them. And I don't care what kind of relationship they are. So that's that query. And if you want to see, I've got some comments in there, but if you want to see what it looks like, it's kind of, it's going to be weird. So I mean, it's just kind of laid out weird, but that's basically what it looks like. Now I probably have comments in there that you don't have, so you don't have to get exactly the same answer. But you can see that on a team, all the arrows are coming in. So basically it's just, let's go pick this. So you can see, for instance, I can start at this fan, go to supports, that fan. I added a relationship. You'll see why in a second. I don't think I actually have to do this, which is called the vicious enemies relationship. And so there's a vicious enemies relationship between Boston and the New York Yankees. And then I can go from there to a comment. So that's 0, 1, 2. So that's what mine looks like. But anyway, that's the query that does that. And then I wanted you to, so that's part 1. So the answer to 1 is this. And we'll just go run that. So that's the query. Make it a little bit bigger. Not that big. So that's the query. What? Okay, well, the question is, how are you going to produce a screen capture of the answer without running the query? So yes, you have to run it. Attach, paste the displayed graph of the answer. Well, that wouldn't. Pictures are better. So, I mean, if you really want to go set up the entire Jupyter environment, run it, then go and embed a graphics package that will then do an overlay, and then you can do all that if you want. But my advice is to just run it in the Cypher, the browser, and then put it in there. So that's 2. 3. So in the schema you created W4111, define a data model that would support the fan, comment on, comment by, supports, follows, in team graph, and provide an ER diagram and the DDL statements for your schema. So I'm actually going to remove things from this one because this exam is getting ridiculous. So you don't actually have to do the schema, you just have to do the diagram. So how would you model this data in a relational database? And the thing is, remember that in a graph DB, nodes and relationships do not have a fixed set of properties. And you may assume that all the property types are strings. So the fact that a node in a relationship, like the comment on relationship or the player node type, don't all necessarily have the same set of properties, what does that tell you? So step 1 is you clearly need to be able to represent a fan, and a fan's got some properties. What is the first thing you would do in the data model? Well, the first thing is you would draw one table. What would you draw? Which table would you draw? All right, so you would draw the fan table. What columns would the fan table have? Right. Any other columns? You can't do this with tables because as soon as you draw a table, I'm going to tell you that I'm going to put a property on fan that you didn't anticipate, which means every time I add a property you didn't anticipate, you have to go back and alter your table. So you're going to say, I'm going to have uni, last name, first name. That's all I have on a fan. All right, I'm going to tell you just this fan has the property deranged professor. And then you go back and alter the table. Then I'm going to give you another one. And I'll keep doing that until you learn your lesson. I don't think very few of you would have got this correct. And then I would have started throwing labels in. Okay, so now this is a fan and a sports writer. So now we're going to have a fan table and a sports writer table. Okay. Some people are fans, some people are sports writers, some people are sports writers and fans. How are you going to do that? This is the answer. That's not the table. That's not it. This is the nucleus of it. And the reason I asked you to do this is there's literally no way to do the loose schema of a graph database by having typed tables. So the natural inclination that everyone has is if I have a node of type fan, I must have a table of type fan. Okay, well, what if they're a fan and a sports writer? So there are people that are fans, people, okay, that's no problem. I'm going to model it as inheritance. But at any point in time, I can add a new label type or I can add a new property. So the answer to this is the way that I would do it. Is, let me put this out of the way. I have a table thing. There's a so I'm just generate a unique ID. In my case, I would just make it an integer. So everything has a generated ID. I could do auto increments, or I could do a UUID. And there's an enum that specifies the thing type. This enum has two values, node and relationship. And then if its type is the enum value is relationship, it's got two other columns, source ID and the target ID. But it only has those if the enum type is relationship. So that is what's the thing coming into this and what's the thing that it points to. And so to do fan, I would have like ID, and then if I link them, I would have another fan, and then if I had follows, I would then have a relationship that pointed to the first one and pointed to the second one. I would then have a relationship to a table of labels, and a label entry's got an ID for the label, and then the thing for which it is a label. And so that way I can have an arbitrary, any instance of thing can have an arbitrary number of labels. And then I do the same thing for properties under the covers. So for each property, there's an ID for that property. There's the thing for which it is a property. There's the property name, and there's the value for that property. And so that under the covers, overly simplistically, is how a graph database represents its data. And this is part of the reason why it's really good at things, because I've got all the properties in one table. So if I express a query on properties, it'll work over all types, whether they're relationships, labels, etc. And then it's easier to follow paths. But anyway, that, yeah, somebody had a question?
Yeah, which is this is almost like the metadata tables that we were making for.
It's similar, yeah. It's not dissimilar from that.
Does this exist for most like graph databases? Like,
Under the covers in a graph database, the nucleus of it is something like this concept. Now, obviously, there's a lot of optimizations, there's a lot of sophistication, but step one in a graph database is something like this. Now, there's more than one guy working weekends on Neo4j, so I'm assuming that inside it, they do more sophisticated stuff than this.
Yeah.
But that's the essence, because remember, there's no types. There's just properties and labels. And any node can have any labels, and any node can have any properties. And I could add a property of any name and any kind. And so this is literally the only way to do it, because if you made a fan table for a fan node, I would start adding labels, taking labels away, adding properties, taking properties away. Same thing for relationships, which is you would say, okay, I'm going to have a relationship table that joins fans and comments. All right, well, I'm going to say, okay, I'm going to have a relationship with that same name that sometimes points to a comment and sometimes points to a diatribe. Okay, well now you've got a relationship from one table in to rows into other tables. And so if you take a step back and you realize what's going on, this is under the covers, what's happening. And this is the only, some version of this is the only way to do it. You cannot make tables for the concrete label types you have. And then the queries on top of that are just querying like, you know, select the thing that's got a property equal to this and a subtype node. And so that's how this thing works under the covers. And I think a lot of you probably would have spent your time kind of banging your head against the wall trying to figure this out, because it's a completely different way to think about it than the way you learn relationally. But this is what's happening under the covers in a graph database. So that's the answer to that. I was going to have, yeah, hang on a second. I was going to have you then load your data model. I'm going to load your data model. So I was going to have you do a bunch of other things, like go take the data from homework 4, put it in the tables you defined, then start writing SQL queries that do joins, etc. But there's already way too much programming on this final, so I'm just going to take those things off. Mostly because I think at least 3/4 of you would have got the model wrong anyway, so what's the point of writing the queries? So just do 1, 2, and 3, which is do the cipher query. Sorry, 2 and 3, do the cipher query, patch the diagram, and then just draw the schema. Don't create the tables. All right. All right, so those are the programming ones. That's the hard part of the exam. The rest of these are written questions. Key compression. What is index key compression? What are the 2 necessary conditions for using index key compression? Anybody know the answer to this? What? That is the correct answer to this. Basically, the idea between index key compression is if, think about the date dimension. So in the dimension table, the date dimension, that index, the primary key on that is basically year, month, and day. Well, a year, this is a simplistic example. If I had that represented as a character string, I could just basically convert the year to a small digit. So I don't have to repeat the 2004 string over and over again. Better example would be, you know, a table, basically a table, salute, a table of people where the index is last name, first name. So the key is going to be last name followed by first name. And if it's in Scotland, all the first names are, last names are Ferguson, so McDougall. Why have those things over and over again? You just have an enum that says 1 is Ferguson, 2 is McDougall, 3 is Murray. And so you've got lots of repeating values. You take the long string representations of the repeating values and replace them by an enum. And then you do a 2-level lookup. That enum points kind of into the nodes that have that value. So one of it is you just replace repeating values with a smaller enum. And then that does the compression. And so you can sort of see that here, which is they took all these red prefixes. So all of the prefixes that are common, they mush them into a common value that typically use an enum. And then from there, you can use the second part of the key to find the ones that you're looking for. So that's key compression. You can compress it by replacing the duplicates. And if there's a fixed number of duplicates, you can replace the duplicate values with an enum. So that's key compression. What are the conditions what are the requirements for key compression? What are the two necessary conditions for using index key compression? The first one is it's got to be a compound key. It's got to be a compound key because what you're doing is you're mucking around with the first segment of the key. And the second one is there's got to be a relatively small number of values for the first part of the key. Because if the first part of the key, every value was unique, there'd be no point compressing the key. So that's key compression, and those are the two requirements for it. What are 3 reasons to use a B+ tree instead of a hash index? If you can't shout out one of them, my life was a complete failure. And I've lost, what? Well, one of them's log and the other one is, but like, why would I use a B+ tree instead of a hash tree? The answer is because it's slower. What? I can't hear you.
Research based on comparison.
Well, they both support comparison, but you're close.
Oh,
What?
compound keys.
Thank God, yes. Hashes are only equality. So when you're, like, if you're doing a select from where, a hash only works for the equality operator, a B+ tree works for the relative comparison operators, greater than and less than. That's reason number 1. Reason number 2 is order by. If I'm going to order the results, it helps to have a B+ tree because a B+ tree is a sorted index. And the third one is that I would pick is range queries, which is a generalization like, please go find everything after 2000 but before 2010. Or like queries, where go find everything where the last name is like FER. So those would be a bunch of reasons to use a B tree. B+ tree is like queries, order, ranges, order by, that kind of thing. A hash only works for exact quality. Give 3 simple examples of rewriting a query to produce an equivalent query. I don't even care what they are, just give me 3 examples. Well, the easiest one is select from A join B is the same as select from B join A. Second one is select from A join B is the same as select from A join select from B. Third one is project select A is the same thing as select project A. Or you could just go Google query, relational query identities, and it'll give you a giant table. On the left side is one query, on the right side is how to rewrite it. So, buffer management. Explain force, no steal, no steal buffer management. Can anybody explain that? Remember, I can't see your screens. So if you wanted class participation points, you would go 3 questions ahead and do this. And then you would basically go, when I get to the question, you would go, Ooh, me. Steal is the possibility of a buffer being stolen by a new transaction. No steal. If we place a no steal policy, then commit abort transactions. All right, so literally, that would be what do. Just go look it up and give an answer. Don't cut and paste the text, just paraphrase it. And if you want, you can reference where you saw the answer. Hash index. Whoops. This is, in this hash index, I inserted in some order 21, 11, 13, 14. So this is a hash. There are 11 entries. Hash tables are almost always prime numbers. So the number of entries in a hash table is almost always a prime number. Because if it's not a prime number, you'll tend to get skews in buckets. Because a number modulo a non-prime number isn't uniformly distributed, whereas it is if it's a prime number. So there are 11 buckets here. That should be the image above. The table size is 11. The hashing algorithm is module the table size, and the rehash function is linear probing. Show the new status of the cache after adding 24 and 30. That's the answer. Another way to do this is okay, that's clearly not the one used. That's not the one used. Oh, it's not a cache, it's a hash simulator. All right, that doesn't look like it, so maybe it's a different one. So you can just look around, make it hash table simulator. If you go back into the lecture notes, the link is actually in there. I just can't remember where I did it. Online hash table visualizer. You can use this one if you want, but basically just go pick an online one. What's the hashing function? Simple modular hash. What's the collision resolution policy? Linear probing. What are the values? Oh, you got to pick the table size. Table size is 11. Basically go pick the values. So it's 11, 13, 14. And we'll actually go and do it beforehand. So it is 11, 13, 14, 21. So I do 11. The table's got 11 entries, 11 modulo 11 is 0. I go 13. So 13. 13's 2. I go in and I add 14. Next. All right, so it's going to add 14, and then it was 21, I guess. 24. All right, so 24 goes there. So 11, 13, 14, 24. 11, 13, 14, it was 21. Oh, 11, 13, 14, 21. It wasn't 24. You're in a lot of trouble. You're in a lot of trouble now. I know, but I needed to load the hash up first. All right. Basically what happens is 24 is 3 modulo 11. So it goes and hits, that's a cache hit, it's a collision. And linear probing says just go through the table until I find an empty space. So that's what linear probing does.
So why not it goes to 1? Why it goes on to-
No, it starts and goes that way. So the hash lookup algorithm is hash. And if it's in that bucket, you're good. Otherwise, start going down the table in order until you either find the thing you're looking for or a blank cell. If you find a blank cell, it's not in the hash. Obviously, if you find it, it is. So 13 is 2 mod 11. 35 is also 2 mod 11. So if I wanted to find 35, I would hash it. It goes to 2, that's 13. Go to the next one, 14. That's not it. Go to 24. That's not it. I hit an empty cell. It's not in the hash. And so that's what linear probing is. So you could just go use one of the online simulators to do that. And so that is hashing with linear probing. And you can see, if you go back to this simulator, there's a lot of hash algorithms. So how do you take something and hash it? And then there's a lot of conflict resolution. You can change the step size on the probe. You can basically do quadratic for probing. So I'm going to const square the number. You can hash the modulo. So I got it. What was the modulo? Hash that. So there's all kinds of ways of doing this. I've never seen anyone. I mean, real database systems will actually change this on the fly based on the data, but I've never seen anyone assign anything other than linear probing. Briefly explain a sort merge join. Briefly explain a sort merge join. Yes, thank you. Briefly explain a. I think I'm gonna. Briefly explain a sort merge join, and when should you use a sort merge join instead of a hash join? A sort merge join is if the left table is got an hash index on the join fields. So select star from customer join known human being on customer dot last name equals known human being dot last name. If I have a sorted index on join, on last name, a sort merge is I go and sort the right table on that column for that key. And then the way I do the join is I go through the left table in order. So basically go through it in the order determined by the key. And since I sorted the right table, I'm not randomly jumping around like I would on a hash, because when it's hashed, Smith hashes to 21, Smythe hashes to 17. So when you're hashing, you're jumping around, which means you may get buffer pool misses. Whereas if the right table is also sorted, if you've loaded Smith, Smythe is probably in the same block. And so what's happening is as you go through the right table, you load a block. And then as you're going through the left table, almost all of the things for a while are in that block. And so if you're going to, if it's in, remember, you always scan the left table. So you're always going to scan that. You've got two choices to optimize on the right side. A bunch of choices, actually. If I build a hash index, it's going to make it easier to find things. I'm not going to have to scan the table, but I might get a buffer pool miss. So I can find the block in constant time, but the block might not be in the buffer pool. Whereas if I sort it, things, when I get a miss, I'm going to load a page, but the next few things on the left side are going to be on that page. And so the answer is, if you're actually using a sorted index on the left side, you're going through it in sort order. On the left side, go sort the data on the right side the same way on the join conditions. Is that clear to everyone? I'll also accept they're really cool. Or he said something in the recitation and I had lost the will to live 45 minutes ago. So, but those are the reasons, is you're always scanning the left table. There are two cases to consider. The scan is going through in some kind of sort order. So it's just already sorted on that value. So I'm going through it in the sort order defined by a key. If I go and sort the right table on that join condition, when I look a key up, if I get a buffer pool miss, I'm going to load the block that has got that value in it. But I know at that point that the next value on the left table is alphabetically related to the one I just loaded. So if it's in there, it's in the block I just loaded. So in essence, you'll do a block IO exactly once for everything on the right table. Whereas, so suppose I have 3 pages of buffer space that I can allocate to the right table, but there are 6 blocks, so I can only have half the right table in at any point in time. When I'm going through a block on the left side, if I have a hash index, they're randomly distributed on the left side. And so that block could be anywhere. So I get a 50-50 chance of getting a buffer pool hit. Whereas if I sort it and store it in sort order, I will only ever read a block once on the right-hand table. So we'll read it once, find everything, and then just go to the next one because I'm going through it alphabetically. So it has vastly fewer block IOs. Everyone understand that? They're cool. He said something about sort will be accepted. Deadlock. Briefly explain 2 techniques a transaction manager may use to break deadlocks. What's the first technique? What? Do people currently have internet connectivity? The answer is they'll build a wait for graph or they'll use timeouts. These are 2. Timeouts are obvious, which is if I say no transaction can run for more than 10 seconds, if I get a deadlock, one of them is going to get aborted. And I'm going to keep, things are going to abort until the deadlock's broken. Wait for graph says if transaction 1 requests a lock that transaction 2 holds, you put a note in the wait for graph. Transaction 1 is waiting on transaction 2. If transaction 2 is already waiting on transaction 3, and transaction 3 is waiting on transaction 1, you've got a cycle in the deadlock graph. In the wait for graph, you've got a deadlock. So the number 1 is it builds wait for graphs and looks for cycles, or it times out and aborts transactions. RAID. What is a major advantage of RAID 5 over RAID 0 and RAID 1? I used a single one. What? I can't hear you. No. You know what you can do is you can just write the Google query you would have entered as the answer to the question. The obvious answer is if I have a block, right? If I have a block, RAID 0 and RAID 1 always store the block twice. So the storage overhead of RAID 0 and RAID 1 is 100%. If I have 100 megabytes of data, I have to store 200 megabytes. If I use RAID 5, the overhead's 25%. So if I have 100 megabytes of data, I have to store 125 megabytes of data. It's the main advantage. That's what it comes down to. Disk addressing. Briefly explain cylinder head sector addressing. A disk has multiple platters. It's like a stack of pancakes. Multiple platters. When you look at it from the side, when you look at it from the top down, it's got tracks. Like racetracks inside racetracks. And a sector is a specific thing is rotating. A sector is kind of a wedge. So cylinder says if I've got a bunch of disks, platters, a specific track, if I go through all the disks as a cylinder. So cylinder basically is how far in or out do I move the head? So if I'm moving it, the head assembly, if I'm moving it in or out and I'm picking a track, I'm actually picking the track on all of them. So that's the cylinder. The head tells me which of the platters and which side of the, if it's on two sides, which side of the platter. And then the sector tells me which wedge of the pie. So if you think about it, you've got a set of like pancakes. You've got to figure out how far to go into the pancake, which pancake you want, and then which wedge of the pancake you want. So that's cylinder head sector addressing. E-tag processing. Briefly explain E-tag processing. It is E-tag processing more similar to pessimistic or optimistic transactions. Somebody Google E-tag processing is when I read a piece of data, what I get back on the read is the data and then a hash value of the data. So I get the data and a hash value of the data. When I write it back on the write operation, I send the new value of the data and the hash I received. The recipient then goes and rereads the data, so goes to get the current value of the data, computes the hash. If the hash is matched, it means the data has not changed, and I perform the write. If the hashes don't match, the data has changed, and I reject the write. So that's all ETAG processing is. When you did the previous problem on optimistic transactions, the version number functioned as the hash. Which is literally all the ETAG is doing is it's sort of a way of determining whether the version of the data that's currently in the database is the same version that you read. Bonus question, who is the greatest hockey player of all time? What? I did. No. Somebody's in a lot of trouble. What did he say? Who said that? Who said that? This is Bobby Orr. If you get it wrong, I won't take points off unless you pick somebody from the Montreal Canadiens, at which point you'll be expelled from college. So the Montreal Canadiens are like the New York Yankees, only French. So Bobby Orr. All right, so we can wrap up for now. These questions, you can Google them. Just don't cut and paste the text. As long as you paraphrase it, it's fine. And if you're really concerned, you can just sort of give a link to where you found the information. So the obvious question is, why did I pick these ones? And the answer is, based on my experience, if you want to convince somebody you're talking to or interviewing with, if you can find a way to work these topics in, it makes you sound like you really understand databases. So these are things that if you can figure out how to work them into an interview, it makes it sound like you really understand databases. Otherwise, when you're 58 years old like I am, and your key data structure is too big, you have a vague recollection that there's a way to make the key data structure smaller, and you go Google, how do I make a key data structure smaller? And you go, oh yeah, I remember that now. So I don't even remember most of this stuff. I just look it up over time. But this, if you think about it, it covered keys and indexes. It covered query rewrite and query optimization. It covered buffer management. Covered disk addressing, transactions. So it kind of touched on all of them. So, I mean, if you can reasonably talk about these things, you're going to sound like you really understand databases, and that's why I picked them. And again, the reason I do the photos is if I just gave you the text, you would just return what I gave you. At least this way, you know, it's not that I really want to watch you type, but you heard everything I said, but when you type it in and actually run it, it just kind of reinforces it. So if you get stuck and your photograph's not correct or something, just let me know. But the hard part on this, you can see when I do it, the hard part is, crap, I spelled the dimension table wrong, or I forgot the name of this column, and so you spend 30% of your time trying to figure out what the query should be, 60% of your time trying to get out the stupid typos, and then 10% actually finalizing the query. I just wanted to eliminate the 60% and the 10% because there's no educational value to that. All right, we're done for the day.
Are you tired? You are.
I've been tired since 1963, so don't let that affect the question.
Yeah, no, like, yeah, it's like you've been having, it's been going on for like
What's your
almost
question?
a year. Okay. I have a little bit of